In the quiet expanse of space, the stars seem so close, yet the journey between them is an unimaginable challenge. The energy barrier to interstellar travel is the ultimate test of physics, where speed, power, and precision collide. From the intense forces inside dying stars to the vast, cold reaches of the galaxy, we explore why reaching the stars is not just a matter of desire, but an energy puzzle that demands our deepest understanding. Join us as we dive deep into the science of what it takes to break through the energy barrier of interstellar travel. Don't forget to like, subscribe, and hit the bell for more in-depth physics explorations. Interstellar travel begins with distance, because distance turns every practical detail into a problem of endurance and energy. The stars appear close in the night sky, yet the nearest ones are separated from the Sun by spans that dwarf the size of the solar system. A spacecraft leaving Earth passes the Moon, then the outer planets, then the scattered bodies beyond Neptune, and still remains inside the Sun's gravitational reach. Sunlight weakens with every step outward, but the Sun continues to shape motion through a long, fading pull. Only after crossing an immense region does the craft truly enter the space between stars, a place that looks empty in pictures but is defined by its scale. Earth's orbit is measured in hundreds of millions of kilometers across. The distance to Neptune is measured in billions of kilometers. These numbers already strain intuition, yet they remain small beside the gap to the nearest star system. A light year, the distance light travels in 1 year, is measured in trillions of kilometers. The nearest star beyond the Sun lies a little more than 4 light years away, and many targets of interest are tens, hundreds, or thousands of light years distant. In these ranges, distance is not only remoteness, it is the length of time a vehicle must function without repair, resupply, or rescue. The first barrier is the time implied by ordinary spacecraft speeds. Most probes that leave Earth travel at tens of kilometers per second, impressive within the solar system, but tiny compared with the speed of light. At such speeds, a journey to the outer planets takes years. A journey to the nearest star takes tens of thousands of years. Doubling speed halves the time, yet it does not change the basic mismatch between solar system travel and interstellar travel. The gulf is so wide that early discussion of starflight often meets disbelief, a reaction sometimes called a giggle factor, where the mind treats the idea as fantasy because the scale is far beyond daily experience. That disbelief has a physical basis. Travel time is not only a human concern, it sets the total exposure of hardware to radiation, micrometeoroid impacts, and slow material aging. It sets the required reliability of navigation and the tolerance for drift. Over a few years, small errors can be corrected with modest fuel. Over centuries, tiny biases in thrust, subtle outgassing, or weak gravitational tugs can accumulate into large deviations. No measurement is infinite in precision, and no control system is free of drift. Distance, therefore, becomes a demand for long-term stability, and stability has an energy cost, because sensing, computing, and correction all require power and mass. Distance also pushes against communication. Signals from a craft at the edge of the solar system already take hours to return. At interstellar distances, messages take years. This delay changes control into planning. Commands must be sent far ahead, and the craft must act with autonomy when conditions differ from expectations. Autonomy adds sensors, processors, memory, and redundancy. Each addition adds mass, draws electrical power, and increases waste heat that must be managed. In this way, distance translates into energy even before propulsion is counted. A mission must also bring along everything it cannot obtain on the way. Near Earth, solar power is abundant and simple. Far from the sun, sunlight falls off sharply and becomes less practical for high power demands. In interstellar space, the sun's light is only one faint source among many. A craft that needs continuous electricity for propulsion, heating, computing, or communication must carry a power system that operates reliably for long durations. The longer the journey, the more the design favors stable output over short bursts, and the more the mission depends on careful energy budgeting. Distance makes propulsion choices stark because motion is not free. A craft must be accelerated from its starting frame, guided along a path, and often slowed near its destination. Each step requires energy. Within the solar system, gravity assists and careful trajectories can reduce propellant needs, but they do not remove the need to change momentum. Over interstellar distances, gravity assists are rare because the craft spends most of its time far from massive bodies. The long cruise dominates the mission, and cruise speed becomes the central trade. Higher speed shortens time and reduces exposure duration, but it demands far more energy to reach and maintain that speed. Lower speed reduces the immediate energy requirement, but it extends exposure time and makes long-term reliability harder. Even the thin interstellar medium matters when distance is large. A craft moving through it encounters atoms, ions, and dust grains. Each encounter is small, but the number of encounters grows with distance. At modest speeds, these collisions are minor. As speed rises, each impact carries more energy and can erode surfaces, damage instruments, and produce heating. Distance, therefore, links directly to shielding, and shielding links back to mass, and mass links back to propulsion energy. The same coupling applies to the power source, thermal control, and redundancy that must survive for the full duration. Distance also affects what it means to arrive. A fast flyby can collect limited data, because instruments have only a short window near the target. A slower approach can extend observations, but it demands earlier planning and longer operation in deep space. If the goal is to match the motion of another star system rather than rush through it, the craft must shed much of the speed it worked so hard to gain. Slowing down requires energy in one form or another, whether by carrying propellant for braking, using magnetic or electric interaction with a medium, or relying on carefully arranged external forces. Each method carries penalties in mass, complexity, or infrastructure. Over interstellar distances, this need to consider both speeding up and slowing down doubles the significance of every kilometre. By the end of this first region, interstellar travel is revealed as a problem defined by scale. The path outward from Earth to the nearest stars is not a short leap, but a long traverse across an environment that gives little and demands much. The energy barrier begins as a distance barrier because distance controls time, and time amplifies every weakness in technology. Beyond the first recognition of distance, interstellar travel meets a deeper boundary that comes from the structure of space and time. In modern physics, motion is not measured against a fixed, universal background. Each observer carries a frame of reference, and the laws that connect energy, momentum, and time remain consistent across those frames. Within this framework, the speed of light in vacuum holds a special place. It is not simply the speed of a beam from a lamp. It is a constant that links how space and time relate, and it sets a limit for how fast information and causality can propagate through empty space. A spacecraft that accelerates in the deep void does not move through a medium in the usual sense. There's no air to push against, no water to part. The ship changes its velocity by exchanging momentum with propellant or with some external field. As the ship's speed rises, the rules of Newtonian motion continue to work well for ordinary conditions, but they begin to diverge from the full description given by special relativity when speeds approach a significant fraction of the speed of light. Special relativity describes how measurements of time, distance, and energy depend on relative motion. Its predictions are confirmed repeatedly in particle accelerators, in precision timing, and in the behavior of fast-moving particles in Earth's atmosphere and beyond. The most immediate consequence for interstellar travel is that the energy required to accelerate an object rises faster than the simple Newtonian estimate as speed increases. At low speeds, kinetic energy grows roughly with the square of velocity. In that familiar regime, doubling speed requires 4 times the kinetic energy. The relationship already grows steep quickly. At relativistic speeds, the growth becomes even more severe because the ship's total energy includes a contribution tied to a factor that depends on the ratio of the ship's speed to the speed of light. As that ratio approaches 1, the factor grows without bound. The ship can continue to gain speed, but each additional increase demands disproportionately more energy than the last. This behavior can be understood without heavy mathematics by focusing on what the ship must accomplish. To change velocity, the ship must change momentum. Momentum increases with speed, but at high speeds, the connection between momentum and energy shifts. Energy becomes increasingly concentrated in the ship's motion relative to the chosen frame. Each unit of added energy produces a smaller increment in speed. The ship's speed can approach the speed of light more and more closely, but it does not reach or exceed it through ordinary acceleration. The barrier is not a wall felt as a force in the ship's cabin. It is an accounting rule of nature that keeps the speed of light as an upper bound for material objects and signals. Time dilation adds another layer. A clock on the moving ship ticks more slowly relative to a clock at rest in the departure frame. This effect is not a trick of observation. It appears in measured differences between atomic clocks flown on aircraft and those kept on the ground. Once gravity's influence is also accounted for, it appears in the extended lifetimes of unstable particles when they move near light speed. For an interstellar craft, time dilation means that the elapsed time experienced on board can be less than the time measured by those who remain near the origin. The magnitude depends on speed. At modest fractions of the speed of light, the difference is small. At higher fractions, the difference becomes significant. Time dilation might sound like a benefit, because it suggests that the crew of a hypothetical fast ship could reach distant stars within a manageable personal time span. Yet the energy cost remains tied to the departure frame's accounting of energy required to accelerate the ship. The ship's engines must still supply the energy needed to change its momentum to that high speed. The ship's power system must still manage the associated waste heat. The ship's structure must still withstand the stress and radiation environment associated with high-speed travel through the interstellar medium. The physics of time does not remove the physics of energy. It only changes how durations compare between frames. Length contraction complements time dilation. Distances along the direction of motion appear shorter in the ship's frame compared with the origin frame. In principle, a ship moving close to the speed of light sees the gap to its destination reduced. This is consistent with time dilation, since both effects are linked by the same underlying relationships. For the ship, a shorter distance combined with a slower ticking of external clocks can make the journey seem shorter. For observers at rest relative to the origin, the ship crosses the full distance in their space, over a long time. Both descriptions match when the full relativistic framework is applied. This consistency does not create new energy. It preserves a coherent picture of the same physical process viewed from different frames. as speed approaches the speed of light. Another inward pressure grows the practical meaning of energy. Any propulsion system must convert stored energy into directed momentum. Chemical reactions do this by releasing energy from rearranged electron bonds, which yields a limited amount of energy per unit mass of fuel. Nuclear reactions access energy stored in the nucleus, releasing far more energy per unit mass. Matter and antimatter annihilation, if it can be controlled, converts mass directly into energy with the highest known efficiency. Special relativity makes clear that mass itself corresponds to energy. The famous equivalence between mass and energy is not a slogan. It is a strict relationship that appears in nuclear power, in the behavior of particles, and in the energy accounting of high-speed motion. It implies that moving large masses to extreme speeds demands energy on a scale that quickly approaches the energy content of substantial amounts of matter. This realization sharpens the energy barrier into a concrete scale. A ship has a certain mass, including structure, payload, shielding, propellant, and power systems. To accelerate that mass to a chosen cruise speed, it must supply a certain amount of energy. If the mission also demands braking at the destination, the energy requirement expands again, because the ship must either carry additional energy and propellant for deceleration or rely on external mechanisms. The relativistic growth of required energy at high speeds turns the choice of cruise speed into a decisive factor. Speeds that seem only a little higher can require vastly more energy when the ship already moves fast. Relativity also affects what the ship encounters. Interstellar space contains atoms and photons in the ship's frame as speed increases. The energy of incoming photons from the direction of travel is shifted upward. A background of low-energy radiation can appear more energetic, and particles in the sparse gas can carry greater effective impact energy. This change is not caused by a hotter environment. It is caused by motion through the environment. The ship's speed transforms the character of what it hits. This transformation increases the demands on shielding and thermal management, tying the speed limit to practical survival as well as to energy accounting. Within this region, the light barrier becomes more than a rule about reaching a number. It becomes a set of linked consequences. Energy grows steeply. Time and distance measures diverge between frames, and the environment ahead becomes more hostile in the ship's own perspective. None of these effects depend on human preference or engineering optimism. They follow from well-tested principles that describe how space and time behave. The ship can still move fast, and it can still cross great distances, but each step toward light speed raises the energy burden and the internal complexity required to handle what that energy implies. Outside the details of any engine, interstellar travel reduces to a single accounting how much usable energy can be carried, generated, directed into motion, and managed as heat. Energy is not only fuel in a tank, it is the ability to do work across time. A spacecraft must power its guidance, its communication, its computers, and its thermal control. It must also supply the far larger demand of changing its velocity by expelling reaction mass or by pushing against some external field. When the journey spans years, decades, or longer, the craft becomes a moving power plant whose central duty is to spend energy carefully and continuously without losing control of where that energy goes. Energy appears in two closely related forms that matter most for travel. One is kinetic energy, the energy of motion. The other is stored energy, held in chemical bonds, in nuclear binding, in electromagnetic fields, or in mass itself. The craft begins with stored energy and must convert part of it into kinetic energy to accelerate. That conversion is never perfect. Some energy ends as heat in engines, power systems, and structures. Some ends as radiation, as sound within machinery, or as random motion of particles in exhaust. Even in a quiet vacuum, these losses remain real because they are internal. They are guided by thermodynamics, the body of physical law that describes how energy moves and why some conversions cannot be fully reversed. The first law of thermodynamics states that energy is conserved. It does not disappear, it changes form. For spacecraft design, this law forces a complete budget. Any energy that fails to become useful thrust still becomes something else, most often heat. The second law of thermodynamics adds direction. It states that processes tend to increase entropy, a measure connected to how spread out energy becomes. In practice, this means that converting stored energy into a tightly directed stream, like a rocket exhaust, always produces some waste heat and disorder. Even an ideal engine that approaches the best possible performance still produces waste that must be carried away. Over time, that waste becomes a limiting factor. A craft that generates high power must also reject heat to remain within safe operating temperatures. In space, heat rejection happens mainly through thermal radiation, the emission of electromagnetic energy from surfaces. There is no air to carry heat away by convection. Conduction is limited to the interior of the craft. Radiators can be built to emit heat, but radiators require area and mass. They also create vulnerabilities because large, thin surfaces can be damaged by impacts or degraded by radiation. The colder the radiator, the less power it can emit for a given area. The hotter the radiator, the more power it can emit, but the closer it pushes materials to their limits. Thermal control thus becomes a quiet but central part of the energy barrier. If a propulsion system demands enormous power for long periods, it demands correspondingly large heat rejection capacity. Energy, in this view, is not only something to obtain, it is something to dispose of safely. The energy barrier is often described as a need for more power, but power and energy are not the same. Energy is the total amount available, while power is the rate at which it is used. A battery can hold a certain energy, but it can only supply a certain power without overheating or failing. A reactor can provide continuous power, but only at a rate limited by its design, cooling, and materials. Interstellar propulsion often demands both large total energy and sustained high power. High total energy alone is not enough if it can only be released slowly. High power alone is not enough if it cannot be sustained for the time needed to reach the desired speed. This distinction becomes clear in the electric propulsion. Electric thrusters can be efficient in how they convert electrical energy into exhaust motion, but they usually produce small thrust. They depend on long operating times to build up speed. If the mission requires rapid acceleration to high velocity, the power system must be enormous, and the heat rejection system must match it. If the mission accepts slow acceleration, the power can be lower, but the system must operate reliably for longer. Either way, thermodynamics shapes what is realistic. Energy density is another inward constraint. Energy density is the amount of energy stored per unit mass or per unit volume. Chemical fuels have a limited energy density because chemical bonds release only a modest amount of energy when rearranged. Nuclear fission releases far more per unit mass. Nuclear fusion promises more still, depending on the reaction. Matter and antimatter annihilation yields the highest known energy density, because it converts mass directly into energy. Yet high energy density does not automatically solve the problem. The stored energy must be converted into thrust with control, and the supporting systems to do that conversion add mass. Storage itself can be hard. Some fuels require extreme temperatures, extreme pressures, or strong magnetic confinement. Some generate radiation that demands shielding. Shielding adds mass, and mass increases the energy required for a given speed. The energy barrier therefore includes not only a source of energy, but also the mass cost of making that source usable. Propulsion introduces another thermodynamic reality. The craft must throw something backward to go forward, unless it uses external momentum exchange. In a rocket, the exhaust carries energy and momentum away. The craft gains momentum in the opposite direction. The efficiency of this exchange depends on exhaust speed. A higher exhaust speed can reduce the amount of propellant needed for a given change in velocity, but producing higher exhaust speed generally requires higher energy per unit mass of exhaust. There is no free path. Lower exhaust speed wastes energy by sending propellant backward too slowly, requiring more propellant mass. Higher exhaust speed requires more energy, which demands a stronger energy source and more thermal management. The choice is a balance that is set by the mission's desired final speed and by how much mass can be devoted to energy and propellant. When the mission aims for a substantial fraction of the speed of light, the energy accounting becomes stark. A modest change in cruise speed can shift the required kinetic energy enormously, even before relativistic effects become dominant. If the craft must also slow down at arrival, the energy required for the full mission grows again. Braking is often as hard as acceleration. A craft that carries its own braking propellant must launch with more mass, which demands more energy to accelerate. This feedback is a classic difficulty in rocket design, where more propellant requires more structure, which requires more propellant, and so on. At interstellar scales, this feedback becomes one of the main reasons the energy barrier feels so severe. Thermodynamics also governs how close a system can come to ideal performance. Engines have efficiencies that describe what fraction of input energy becomes useful output. Perfect efficiency is not achievable for real heat engines because some energy must be rejected as waste heat. Even systems that are not classical heat engines still face losses in electrical resistance, friction in moving parts, imperfect magnetic confinement, and radiation from hot components. Over long durations, small inefficiencies become large heat loads. A craft can plan for these with radiators and careful design, but the plan must remain conservative because overheating can destroy electronics, weaken structures, and degrade fuel systems. In this region, energy is revealed as the true currency because it touches every subsystem. It determines how fast the craft can go, how long it can accelerate, how much mass it can carry, how much shielding it can afford, and how it can survive its own waste. The barrier is not a single obstacle. It is the sum of conservation, irreversibility, and heat. These laws do not prevent interstellar travel in principle, but they set a strict price. Any credible path must pay that price in stored energy, in power systems, in thermal control, and in mass that is carried across the long dark between stars. From the broad idea of energy as currency, the next region narrows to a way of measuring what a civilization can realistically attempt. A spacecraft is built by people living on a planet with limited resources. The planet receives a steady flow of energy from its star, and it contains reserves of chemical fuels and nuclear fuels. Its inhabitants can collect energy in power plants, convert it into electricity, store it, and use it to move mass. Yet there are limits to how much energy can be controlled at once, how efficiently it can be directed, and how much infrastructure can be devoted to a single project. The scale of energy control becomes a rough predictor of the scale of travel that becomes possible. One widely used yardstick is the Kardashev scale, which categorizes civilizations by the total power they can harness. The idea is simple in outline. A civilization at the first level can use energy comparable to the total power available on its home planet. A civilization at the next level can use power comparable to the total output of its star. A civilization at the next can draw on power comparable to the output of its galaxy. The categories are coarse, and the actual boundaries are not rigid. Still, the scale provides a way to think about interstellar travel without pretending that engineering happens in isolation from energy infrastructure. A planet-based civilization draws energy from sunlight, wind, water flow, fossil fuels, geothermal heat, and nuclear fuels. Most of these sources are limited by practical collection and conversion. Sunlight is abundant but spread out. Collecting it at high power requires large areas and efficient conversion. Fossil fuels contain stored chemical energy, but are finite and produce waste products that can alter a planet's climate and chemistry. Nuclear fission provides high energy density but produces radioactive byproducts and requires careful containment. All of these constraints mean that the power a civilization controls is not only a matter of physics, it is also a matter of technology, economics, and environmental management. Yet in the context of interstellar travel, the key point is that present-day capabilities remain far below the power scale associated with fully star-level engineering. A planetary-level civilization can build impressive machines, including rockets that reach other planets, probes that cross the outer solar system, and observatories that study distant galaxies. It can also build particle accelerators that probe fundamental physics. These achievements show that physical law does not prevent advanced control of energy. However, the total power devoted to spaceflight remains small compared with global energy use. Most energy on a planet is used for heating, cooling, transportation, manufacturing, and food production. Space missions receive a fraction. Even when a single mission is ambitious, it is usually constrained by budgets, by schedules, and by the limits of launch systems. Interstellar travel challenges these proportions. A vehicle that carries enough energy to reach high speed, plus the mass to manage and direct that energy, quickly approaches the scale of national or global energy projects. If the craft must accelerate a large payload to a high fraction of the speed of light, the required energy can become comparable to the annual energy consumption of a planet-level civilization, depending on the details. This comparison is not a dramatic flourish. It is a direct consequence of the kinetic energy associated with high velocity and large mass, and of the inefficiencies and mass penalties of real propulsion. When energy demands approach the scale of planetary output, the project becomes more than a spacecraft. It becomes a civilization-scale system. The Kardashev scale also highlights a key distinction between carrying energy and using external energy. A craft that carries its own fuel must lift that fuel out of a gravity well and keep it stable for long periods. A craft that uses external energy, such as a sail pushed by light from a distant source, shifts the burden. The craft can be lighter because it does not carry all the energy on board. The energy generation and directing infrastructure remains near the origin, where mass can be supported by a planet's surface, repaired, and expanded over time. In this approach, interstellar travel becomes a problem of building and maintaining a powerful energy source and a precise beam system rather than packing everything into a single vehicle. Such infrastructure begins to resemble the capabilities of a higher Kardashev level. For example, building a laser array capable of pushing a sail to extremely high speed would require collecting and directing enormous power. The array would likely be spread over large areas, potentially in space to avoid atmospheric absorption and turbulence. It would require precise phasing, tracking, and maintenance. The energy use would be concentrated in time and direction. This is closer to star-level engineering in spirit, even if not in total power use. It shows why the scale is useful. It connects the idea of propulsion directly to what an energy-harvesting civilization can do. There are uncertainties in how to interpret the scale in real terms. Civilizations might develop energy sources that are more efficient, less polluting, and more compact than present-day systems. They might spread energy collection into space with large solar arrays, use advanced nuclear systems, or develop entirely new methods that remain consistent with physics but are not yet practical. Observations of exoplanets do not currently reveal clear signatures of star-spanning engineering in nearby systems, though the search for technosignatures is ongoing and inherently difficult. The absence of evidence does not prove absence of advanced engineering, but it does underscore that the step from planetary engineering to star-level engineering is large. Within this region, the energy barrier becomes a question of civilization capacity. A rocket equation on paper can suggest a trajectory, but the required energy and infrastructure may exceed what a planet can spare. A feasible interstellar mission must either accept very long travel times at modest speeds, or it must be supported by energy systems far beyond current global capacity, or it must use external energy sources with immense stationary infrastructure. The scale does not declare interstellar travel impossible. It locates it on an energy ladder that explains why it remains out of reach today, and why different propulsion concepts imply different levels of societal and industrial commitment. After the measure of civilization-scale energy, attention returns outward to the propulsion methods that fit within a planetary level of capability. These are sometimes called Type 0 technologies, not as a formal category, but as a reminder that they rely on energy sources and engineering that are available without star-scale infrastructure. They are the tools that have already carried machines to orbit, to the moon, and across much of the solar system. They define what can be done with present-day physics and with technologies that either exist now or are plausible extensions of existing systems. Chemical rockets are the most familiar. They store energy in chemical bonds and release it through combustion, heating gases that expand through a nozzle to produce thrust. The strength of chemical propulsion is its high thrust. It can lift heavy payloads quickly and escape planetary gravity. Its weakness is limited energy density. Chemical reactions release only a modest fraction of mass energy, and the exhaust speed is limited by the temperature the engine can tolerate and by the molecular mass of the exhaust. Because of this, chemical rockets require large amounts of propellant to achieve large changes in velocity. This becomes severe when the mission demands speed far beyond what is needed to reach orbit or to travel between planets. Within the solar system, chemical propulsion is often combined with gravity assists. A spacecraft can pass close to a planet and exchange momentum with it, stealing a tiny amount of the planet's orbital energy and changing its own trajectory. This method has enabled missions to the outer planets with limited propellant, yet gravity assists are tied to the arrangement of planets and to the craft's ability to survive close approaches. They cannot be used continuously. They are not available in the interstellar void. Even within the solar system, they cannot raise a craft's speed to a meaningful fraction of the speed of light. They are clever, but they do not change the underlying energy content of chemical fuel. Electric propulsion offers a different trade. Ion engines and related systems use electrical power to accelerate charged particles to high exhaust speeds. The thrust is small, but the efficiency can be high, because the exhaust leaves much faster than in chemical rockets. This means that less propellant mass is needed for a given change in velocity, provided the craft can supply the electrical power for long durations. Electric propulsion is well suited to deep space missions that can accept slow acceleration over months or years. It is not well suited to rapid departure from Earth's surface because its thrust is too low to overcome gravity for large payloads without enormous power. For Type 0 capabilities, the power source for electric propulsion is often solar arrays or radioisotope power systems. Solar arrays work well near the Sun but provide less power as distance increases. Radioisotope systems provide steady power for many years but at relatively low power levels. Larger power systems, such as nuclear reactors, can provide more electrical power. Reactor concepts have been studied and some have been used in space at modest scales. A reactor can enable higher power electric propulsion, but it adds mass and requires shielding and cooling. It also introduces engineering challenges in reliability and safety. Another Type 0 idea is electromagnetic launch or mass drivers, which accelerate payloads using electric or magnetic fields rather than chemical combustion. On a planet or a large space structure, a long track could in principle accelerate a craft to high speed before it leaves the launch system. This approach shifts energy supply to the ground or to a large platform where power generation can be larger and where heavy infrastructure can be supported. It also reduces the need for onboard propellant during initial acceleration. Yet electromagnetic launch faces limits. The track must be extremely long to keep acceleration within tolerable bounds for structure and payload. Atmospheric drag and heating limit what can be done from a planet's surface. A space-based launcher avoids the atmosphere but requires massive construction and precise control. Even a very large launcher, within planetary resources, is unlikely to impart velocities that make interstellar travel practical on human timescales, though it could contribute to high-speed probes within the solar system. Type 0 approaches also include gravitational and solar sailing, in which a large reflective or absorptive surface uses momentum from sunlight to produce a small but continuous push. Solar sails require no propellant and can operate for long periods, but the available thrust is weak and declines with distance from the Sun. Over time, a sail can build speed, and clever trajectories can use close passes near the Sun to increase the push. Still, the energy flux of sunlight sets a limit. Without an external concentrated beam, a solar sail remains a slow method for reaching interstellar distances. In evaluating Type 0 propulsion, the energy barrier appears in a practical form, the mismatch between achievable exhaust speed, available power, and desired cruise velocity. Chemical rockets can deliver high thrust but carry limited energy per unit mass. Electric propulsion can deliver high exhaust speed but requires sustained power and long operating times. Nuclear power can increase available energy and power, but adds mass and complexity and introduces thermal and radiation management burdens. Ground-based or platform-based launch systems can reduce onboard fuel but demand immense construction and still face limits in achievable speed. Uncertainty appears not in the basic physics but in engineering and economics. It is known that chemical propulsion cannot reasonably accelerate large masses to relativistic speeds because the propellant requirements become overwhelming. It is known that electric propulsion can achieve high efficiency but is power limited. It is known that nuclear systems could provide higher energy density, but their practical implementation in space at large scales remains challenging, and the massive shielding and radiators can dominate designs. The uncertainty lies in how future engineering might improve specific components, such as lightweight radiators, high-temperature materials, or compact reactors with long life. Even with optimistic improvements, Type 0 methods still face the core energy scaling that makes interstellar travel difficult. Within this region, the barrier takes on a modest but important shape. Type 0 propulsion can send probes outward, possibly even to the farthest reaches of the Sun's influence within manageable timescales. It can also, with patience, send small craft toward the nearest stars on very long journeys measured in thousands of years. What it cannot do is compress interstellar travel into short durations for substantial payloads without moving beyond the energy resources and infrastructure typical of a planetary civilization. The path inward therefore continues by examining how propulsion performance is measured and how sustained thrust and exhaust speed govern the energy cost of leaving the solar system behind. Within the domain of near-term propulsion, the most revealing measure is not dramatic thrust at launch, but the relationship between exhaust speed, propellant use, and time under thrust. Engineers often summarize this relationship with a term called specific impulse, which is a way of describing how effectively an engine uses propellant to produce momentum change. The name can be technical, but the meaning is simple. A propulsion system is more effective when it can push a craft using less propellant for the same change in velocity. This effectiveness depends strongly on how fast the exhaust leaves the engine. Faster exhaust means each unit mass of propellant carries more momentum away, allowing the craft to gain more momentum per unit propellant. In chemical rockets, exhaust speed is limited by chemistry and by the materials that must contain high temperatures and pressures. Hot gases expand through nozzles, and the engine's performance is tied to how hot those gases can be and what molecules they are made of. There are improvements through better fuels, better nozzles, and staged combustion, yet the basic ceiling remains set by the energy available in chemical bonds. This is why chemical rockets tend to deliver strong thrust for short periods, while consuming large propellant masses. They are powerful for leaving a gravity well, but they become inefficient for extremely large velocity changes. Electric propulsion flips the pattern. It can produce exhaust at far higher speeds by using electromagnetic fields to accelerate ions or plasma. The propellant can be used slowly, and the exhaust can leave with far greater speed than hot chemical gases. This means the craft can achieve a larger total change in velocity for a given propellant mass. Yet the thrust is small because the engine is not throwing mass backward very quickly in terms of kilograms per second. The engine is efficient in energy use per unit momentum change, but it delivers that change gradually. This is where sustained thrust becomes a central idea. Sustained thrust is the ability to apply a small acceleration continuously for a long time. A small acceleration seems insignificant over seconds, but over months and years it can accumulate into large speeds. The physics is patient. If an engine produces a tiny push day after day, the craft's velocity slowly grows. This growth can outpace a short burst from a high-thrust engine if the total time under thrust is long enough. For interplanetary missions, this approach can reshape trajectories. For interstellar ambitions, it becomes one of the few pathways that does not demand immediate key, concentrated energy on a scale that overwhelms a mission. Time under thrust, however, is not free. An engine that runs for years must be reliable for years. Power electronics must remain stable. Thrusters must resist erosion from high-energy particles and from their own plasma. Propellant feed systems must avoid clogging and contamination. Guidance and navigation must remain accurate across long spans. Each of these needs adds redundancy, monitoring, and safe operating margins. These additions increase mass and power demands, feeding back into the propulsion problem. A slow engine that runs for a very long time can succeed only if the entire spacecraft is designed as a durable system rather than a short-lived vehicle. Sustained thrust also shifts the energy problem from total energy to power and heat. An electric thruster might require steady electrical power for years. If the power comes from solar arrays, the available power declines with distance from the Sun, so acceleration weakens as the craft travels outward. If the power comes from a nuclear source, the craft must carry a reactor or radioisotope system, along with shielding, conversion equipment, and radiators. The engine may be efficient, but the overall system efficiency includes the power source and its heat losses. Electrical generation produces waste heat that must be radiated away. A spacecraft that relies on long-term high power must therefore carry large radiators and maintain them for the full mission. The connection between exhaust speed and energy becomes clearer when considering what it takes to accelerate propellant. To throw propellant backward at high speed, the engine must give that propellant kinetic energy. The higher the exhaust speed, the more energy per unit mass the exhaust carries. This energy does not come from nowhere, it comes from chemical reactions, nuclear reactions, stored electric energy, or an external power beam. Increasing exhaust speed can reduce propellant mass, but it increases the energy required to accelerate each kilogram of propellant. For a given mission speed, there is a balance. Too low an exhaust speed wastes propellant mass. Too high an exhaust speed demands huge energy input and large power systems. The optimum depends on the mission goals, the available power, and the mass penalties of the energy system. This balance also reveals why interstellar travel is often described as an energy barrier rather than only a propellant barrier. A craft that aims for very high cruise speed needs a large total change in velocity. Achieving that change with a rocket requires expelling propellant. If the exhaust speed is modest, the craft must expel a large mass of propellant. Carrying that propellant increases the starting mass, which increases the energy needed to accelerate the entire vehicle. If the exhaust speed is very high, the craft can carry less propellant, but it must have an energy source capable of giving the exhaust that speed. The energy source adds mass and demands heat rejection. In both cases, the barrier appears as a coupling between mass and energy. Sustained thrust adds a further coupling with time. If a craft accelerates slowly for a very long time, it can reach higher speeds without demanding extreme power. Yet the longer it accelerates, the longer it must also manage its own systems. It must keep propellant from freezing or boiling, depending on storage. It must keep electronics within temperature limits despite a changing external environment. It must maintain communication across increasing distances. It must resist the gradual damage caused by radiation and particle impacts. This long-duration operation is itself an energy cost because it requires continuous power for heaters, control systems, and communication. Even a small average power draw becomes a large total energy requirement over decades. For interstellar travel, the choice of whether to accelerate continuously or in bursts shapes everything that follows. A burst approach concentrates stress and power demands. A continuous approach spreads them out but demands long life. There is no option that avoids the relationship between desired final speed and required energy. The only freedom lies in how that energy is supplied over time, and how much mass and complexity the craft can afford to carry to make the energy usable. In this region, the engine is no longer judged only by how much thrust it can produce. It is judged by how it spends propellant, how much power it demands, and how long it can keep operating without failure. Specific impulse, understood as a measure of propellant efficiency linked to exhaust speed, becomes a lens that shows why ordinary rockets are effective for leaving planets, but struggle with the vast velocity changes implied by interstellar missions. Sustained thrust becomes a lens that shows why low-thrust engines can, in principle, build high speed over time, yet only if the spacecraft becomes an unusually durable, power-rich system. The energy barrier therefore tightens around a practical truth: reaching the stars is not only a matter of pointing outward, It is a matter of sustaining controlled energy conversion, day after day, long after the sun has become a distant light behind the craft. Electric propulsion becomes most visible as a style of travel rather than a single machine, because it trades force for patience. In this approach, the spacecraft carries a supply of propellant, often a heavy inert gas, and uses electrical power to strip electrons from atoms, creating ions. Those ions are then accelerated by electric fields to very high speeds and expelled backward. The thrust is small because the mass flow is small, yet the exhaust leaves so fast that each kilogram of propellant carries away substantial momentum. Over long spans, that momentum exchange accumulates into large changes in velocity, and the spacecraft's path becomes the slow result of continuous, carefully metered energy use. The inner reality behind the calm push is the power system. Electric thrusters do not create energy. They spend electrical power to accelerate propellant. The thrust produced is tied to how much power is available and to how efficiently the thruster converts that power into directed exhaust motion. A higher exhaust speed usually means the engine gives more energy to each ion, which can reduce the needed propellant mass for a given mission change in velocity. Yet giving more energy to each ion does not by itself increase thrust, unless more ions are also expelled per unit time. Increasing both exhaust speed and ion flow pushes the power requirement upward. The power system then becomes the main limiter, because it must deliver electricity reliably while remaining within mass and thermal constraints. Near the Sun, solar arrays provide the most common power source for electric propulsion. Sunlight at Earth's orbit is strong enough that large panels can support meaningful electrical output. The panels convert a fraction of incoming light into electricity and warm the rest as heat. They must point appropriately, survive radiation, and endure micrometeoroid impacts. Even when these challenges are met, sunlight weakens rapidly with distance. As the spacecraft travels outward, this same panel area receives far less light, electrical output falls, and the thrusters must reduce power or shut down. The journey then becomes a pacing problem. The craft accelerates more strongly in the inner solar system and less strongly farther out. Its final speed depends on how long it can thrust while power remains sufficient, and on how it manages the diminishing energy income from the sun. This decline shapes the practicality of solar electric propulsion for interstellar ambitions. A craft can, in principle, use solar power to spiral outward and build velocity over years, yet there is a point where sunlight becomes too weak to justify the mass and area of arrays. At that point, the craft either coasts or depends on a different power source. Coasting preserves speed but does not increase it. To keep accelerating in deep space, the craft needs a power system independent of sunlight. Radioisotope power systems provide steady electricity from the heat produced by natural radioactive decay. They can operate for many years with few moving parts, and they have powered deep space probes where reliability matters more than high output. Their limitation is power. The electrical output is modest, and it declines as the radioisotope decays. For electric propulsion, modest power means modest thrust. A spacecraft can still accumulate velocity, but the acceleration becomes extremely small, and the time required to reach high speed becomes very long. The system works well for some solar system missions where propellant efficiency is valuable and time is less constrained. It does not easily scale to fast interstellar travel for substantial payloads. Nuclear reactors offer higher power and more flexibility. A reactor can produce heat at a controlled rate and use a conversion system to generate electricity. In space, conversion might use turbines, thermoelectric elements, or other approaches. Every method produces waste heat, and waste heat must be rejected by radiators. The radiators must be large enough to emit the heat without overheating the system. This requirement becomes central because high electrical power implies high rejected heat, even for efficient conversion. The reactor also produces radiation that can damage electronics and harm biological systems. Shielding can reduce exposure in chosen directions, but shielding adds mass. A design that delivers high electrical power for long durations therefore carries a burden of mass in reactor structure, shielding, and radiators. That mass reduces the acceleration produced for a given thrust and increases the energy needed to reach a given final speed. The pacing of an ion-driven craft is also shaped by thruster lifetime. Ion engines and Hall thrusters operate by guiding plasma and accelerating charged particles. Over time, energetic ions strike internal components and erode them. Materials sputter away atom by atom. Magnetic and electric field geometries must remain stable despite erosion. Propellant feed systems must remain clean. If the mission demands years of continuous thrust, the thrusters must be designed for endurance. This can be achieved through careful materials and geometry, but it adds complexity. A mission might carry multiple thrusters, using them sequentially. That adds redundancy, but redundancy adds mass, and mass increases the required energy for any target speed. There is also the question of propellant itself. A heavy noble gas is often chosen because it is easy to ionize and provides good momentum per ion. Storing such propellant requires tanks and pressure management. Tanks add mass, and they must remain intact under thermal cycling and radiation exposure. Over long missions, valves and regulators must work without leaks. Any loss of propellant reduces the attainable change in velocity. The propulsion system becomes an integrated chain in which power availability, thruster performance, propellant storage, and thermal control all limit each other. When this system is placed against the scale of interstellar travel, the core difficulty is not that ion engines are inefficient. They can be efficient in propellant use. The difficulty is that high final speed demands either very long thrusting or very high power, and both carry heavy costs. Long thrusting requires extreme reliability and a steady power supply for decades. Very high power requires reactors, large radiators, and heavy structural support, all of which increase mass. The energy barrier reappears as the mass of the power plant needed to keep the engine running while the ship is still accelerating. A related idea is beamed power, where an external source sends energy to the spacecraft, which converts that energy into electricity or directly into propulsion. This approach keeps the power plant near the origin. It reduces onboard power mass but introduces a different pacing constraint. The spacecraft must remain within the reach and focus of the beam. Over increasing distances, beam spreading and pointing accuracy become difficult. The receiving system on the spacecraft must be large enough to capture useful power and robust enough to survive heating. The conversion of received energy into thrust still produces waste heat that must be rejected. The idea changes where the energy comes from, but it does not remove the thermal and structural costs of using that energy. Electric propulsion therefore defines a corridor of practicality. It excels where a spacecraft can accept small thrust over long time, where electrical power is available at manageable mass, and where mission speeds remain far below relativistic regimes. It supports deep space missions that gradually reshape orbits and that carry science payloads with careful energy budgets. It can, with sufficient time, reach higher speeds than chemical rockets for a given propellant mass. Yet when the goal becomes interstellar travel in short times, power becomes the bottleneck, and the ship's power plant grows until it dominates the design. Within this region, the steady ion plume becomes a symbol of controlled energy use, but also a reminder that space is unforgiving of waste. Every watt sent to a thruster must first be generated and then managed as heat when it fails to become directed exhaust energy. Every kilogram added to support power production demands more momentum change. Electric propulsion shows that a spacecraft can move far with small propellant mass. Yet it also shows that speed is expensive not only in fuel, but in sustained power. The deeper barrier is not the lack of clever thrusters. It is the challenge of carrying or receiving enough steady power for long enough, while keeping the spacecraft cool, intact, and precisely controlled as it slowly builds the velocity needed to leave the Sun's neighborhood behind. When nuclear fission enters the picture, the energy barrier shifts from the scarcity of power to the cost of carrying power safely. Fission releases energy when heavy atomic nuclei split into lighter ones. A small amount of mass is converted into energy, and the released energy appears as heat and as energetic particles and radiation. On Earth, fission reactors use this heat to make steam and drive turbines, or to generate electricity by other means. In space, the surrounding vacuum changes the engineering but not the underlying physics. The reactor still produces heat that must be converted into useful power, and the remainder must be rejected. The reactor still emits radiation that must be managed. The reactor still requires control systems that keep the chain reaction stable for long durations. The chief attraction of fission for space propulsion is energy density and continuity. Fission fuel contains far more usable energy per unit mass than chemical fuels. A reactor can operate steadily for years, providing a reliable source of heat and electricity. This steadiness makes it compatible with long-duration electric propulsion, where the engine needs continuous power. It also makes it compatible with systems that require sustained onboard electricity for life support, communications, and thermal regulation. In principle, a fission-powered spacecraft could accelerate for a long time, slowly building speed without depending on sunlight. The first inward constraint is the conversion from heat to thrust. A reactor produces heat. To propel a spacecraft, that heat must be turned into a directed momentum exchange. One route is to convert heat into electricity and then use electric thrusters, as in nuclear electric propulsion. Another route is to use the reactor's heat directly to heat a propellant and expel it through a nozzle, as in nuclear thermal propulsion. In nuclear thermal propulsion, the reactor heats a working fluid, often hydrogen, to very high temperature. The hot gas expands through a nozzle, producing higher exhaust speed than chemical rockets can typically achieve because the temperatures can be higher and the working fluid can be lighter. This improves propellant efficiency compared with chemical rockets, but it does not escape the basic scaling of rocket propulsion. To reach very high speeds, large mass ratios are still required, and carrying all the propellant in the reactor still imposes heavy mass. Nuclear electric propulsion can achieve higher exhaust speeds than nuclear thermal propulsion, because electric thrusters can accelerate ions to extreme velocities. Yet nuclear electric propulsion requires conversion equipment generators, power electronics, and transmission lines, all of which add mass and complexity. The conversion process also produces waste heat. Even if a reactor is efficient, a large fraction of the generated heat must be rejected. In space, rejecting heat means radiating it away, and radiators must be large enough to emit the required power. The need for radiators grows rapidly with reactor power. A modest reactor can be paired with manageable radiators. A high-power reactor can demand radiators so large that they dominate the spacecraft's size and vulnerability. Radiation is the next inward constraint. A fission reactor emits neutrons and gamma rays. These forms of radiation can damage materials, degrade electronics, and harm biological tissue. Shielding can reduce exposure, but shielding is heavy. Designers can place the reactor at the end of a long boom and put the payload far away, using distance as a form of shielding because radiation spreads out. They can also shape the shielding so that it blocks radiation in the direction of the crew or sensitive instruments while leaving other directions less protected. This can reduce mass compared with fully surrounding the reactor, yet even directional shielding and structural separation add mass and structural complexity. The boom must be stable. The craft must control its attitude so that the shield remains between the reactor and protected zones. These demands tie back into guidance and control energy use. There is also the question of reactor stability over long missions. Reactors on Earth are monitored continuously and can be serviced. A spacecraft reactor must operate with high autonomy and low maintenance. It must handle changes in heat rejection conditions, changes in power demand, and potential faults. Control rods or other mechanisms must move reliably. Materials must resist radiation damage that can cause swelling, embrittlement, and changes in thermal conductivity. Cooling channels must remain open. These are known engineering challenges, and solutions exist in principle, but scaling them to very long missions with minimal mass remains difficult. Fuel supply and safety add further mass. A reactor needs enough fission fuel to last the intended operating period at the chosen power level. It needs a reactor core that can handle heat flow without melting. It needs a coolant system that moves heat from the core to the conversion or propulsion components. Coolants can be gases, liquids, or molten metals, each with trade-offs in temperature range, mass, and reliability. Pumps can be a point of failure. Passive circulation can reduce moving parts but may limit power density. Each choice affects the reactor's mass and the craft's thermal design. A nuclear system also changes the mission's risk profile. Launching a reactor fuel supply from Earth requires careful containment to prevent dispersal in an accident. Some designs propose launching the reactor in an inert state and only starting it after reaching a safe orbit. This reduces risk but adds procedural complexity. These considerations do not alter the physics of energy, but they shape what designs are likely to be pursued. When fission propulsion is considered for interstellar missions, the central issue becomes scale. A reactor powerful enough to drive a spacecraft of very high speed in a reasonable time would likely be very large, both to manage heat and to provide shielding. The added mass would reduce acceleration and increase the total energy required for the mission's target speed. A smaller reactor reduces mass but also reduces power, stretching acceleration over longer times. The resulting velocities may still be far below what is needed to reach another star within short durations. Fission can transform solar system travel, enabling faster outer-planet missions and more capable deep space operations. It can also serve as a stepping stone for high-power systems in space. Yet as a direct path to rapid interstellar travel, fission remains constrained by the coupled demands of reactor power, radiator area, shielding mass, and long-term reliability. Uncertainty remains in how lightweight future reactors and radiators can become, and in how much power can be sustained in space without excessive mass. Advances in high-temperature materials could allow higher radiator temperatures, reducing required area. Advances in reactor design could improve power density. Still, the second law of thermodynamics continues to enforce waste heat, and radiation continues to enforce shielding or distance. These are not engineering details that can be ignored. They are intrinsic to the process of extracting nuclear energy. Within this region, fission appears as both an opening and a tightening. It opens a path beyond chemical limits by providing far greater energy density and steady power. It tightens the barrier by imposing heavy requirements in mass devoted to heat rejection and radiation protection. The reactor is not only a fuel source, it is a complex, massive system that must be carried across interstellar distances. In the quiet accounting of interstellar travel, fission shows that finding more energy is only half the story. The other half is paying the mass and thermal costs of using that energy safely, continuously, and under control as the spacecraft tries to gather enough speed to leave the sun far behind. As propulsion concepts push beyond fission, attention turns to fusion, a process that powers stars and offers the promise of far greater energy release per unit mass than chemical fuels. Fusion releases energy when light nuclei join to form heavier nuclei. In the simplest picture, two nuclei approach closely enough that the strong nuclear force binds them together, and the resulting nucleus has less mass than the originals. The difference appears as energy, often carried by fast particles and radiation. On Earth, fusion is difficult because positively charged nuclei repel each other, and extreme conditions are needed to overcome that repulsion. Yet the attraction of fusion for space travel remains steady because the potential energy density is high, and the reaction products can, in principle, be directed to produce thrust. In interstellar discussions, a specific fusion idea often appears as a way to avoid carrying huge propellant masses. It is the concept of a ramjet, where a spacecraft collects fuel from its surroundings during flight. The interstellar medium contains mostly hydrogen and helium, spread thinly as atoms and ions. If a craft could gather this material efficiently, compress it, and fuse it, it would have a continuous fuel supply. The craft would not need to launch with all its reaction mass on board. In theory, it could accelerate for long periods, limited mainly by its ability to harvest, confine, and burn the incoming gas. The first inward barrier is the density of interstellar gas. The space between stars is not empty, but it is extremely sparse by terrestrial standards. In many regions, the number of particles in a cubic centimetre is only a few, sometimes less. Even in denser clouds, the density remains thin. For a craft to collect a significant mass flow from such a medium, it must sweep through a vast volume each second. At low speed, the swept volume per second is limited, and the collected mass is tiny. At high speed, the swept volume increases, but the engineering stress and heating from impacts also increase. The collector, often imagined as a magnetic scoop spanning many kilometers, must interact with ionized hydrogen and guide it toward the craft. This requires strong magnetic fields extended over large distances, and those fields require energy and structure. Magnetic collection is often chosen in concept because charged particles respond to magnetic fields without physical contact. Yet the interstellar medium is only partly ionized, and neutral atoms do not respond in the same way. Ionizing neutral hydrogen requires energy, even for ions. Guiding and compressing a thin stream into a dense target region demands careful field geometry and stable power. The scoop must also remain aligned as the craft moves, because a slight misalignment could reduce collection or produce uneven loads. These requirements turn the ramjet idea from a simple fuel-gathering concept into an immense electromagnetic system that must operate continuously. Compression is the next barrier. Fusion does not occur simply because hydrogen is present. The nuclei must be brought into close interaction under high temperature and pressure, or under confinement conditions that achieve similar effects. A spacecraft collecting hydrogen from interstellar space starts with a very cold, diffuse gas relative to fusion requirements. Bringing that gas to fusion conditions demands energy, and the energy must come from somewhere. If the craft is already moving fast, the incoming hydrogen arrives with substantial kinetic energy in the craft's frame, which can be converted into heat. This might seem helpful, yet it also creates a problem because converting that energy into useful compression without destroying the collection system is difficult. The incoming particles carry momentum that must be managed, and the act of collecting them creates drag. The craft gains propellant but also slows unless the collected material is quickly turned into thrust with greater momentum in the opposite direction. This leads to a central inward constraint a ramjet must overcome its own collection drag. To accelerate, it must produce more thrust than the decelerating effect of gathering and compressing the medium. At low speeds, the collection rate is low and drag is modest, but thrust is also limited because there is little fuel flow. At high speeds, the fuel flow increases, but the drag and heating rise sharply. The system must find a regime where net thrust remains positive while the scoop and confinement system survive. Whether such a regime can exist for realistic engineering remains uncertain, and the uncertainty is rooted in the coupled physics of plasma interaction, magnetic field strength, and heat management. Fusion itself presents further constraints. The most accessible fusion reactions in laboratory settings often involve isotopes of hydrogen, such as deuterium and tritium. These reactions can release significant energy at comparatively lower temperatures than other fusion options. But tritium is rare and radioactive, and it must be bred or carried. Interstellar hydrogen is overwhelmingly ordinary hydrogen, which requires proton-proton fusion to use directly. Proton-proton fusion is the process that powers the Sun, but it is extraordinarily slow at accessible densities because it proceeds through a weak interaction step. In the Sun, the enormous density and long timescales make it viable. In an engine, the reaction rate would be far too low to provide thrust unless confinement and density were extreme. This pushes realistic fusion propulsion concepts toward carrying specialized fuels rather than relying solely on interstellar hydrogen. If a spacecraft carries fusion fuel, the mass advantage over fission remains significant, but it does not remove the need for reaction mass. The craft must still expel something backward. Fusion reactions release energy primarily in fast particles, and those particles can, in principle, be directed by magnetic fields to form an exhaust. Yet many reactions also produce neutrons, which carry energy away without responding to electromagnetic control. Neutron energy becomes heat in surrounding structures and shielding. This is both a loss of useful thrust energy and a source of waste heat and radiation damage. Reactions with fewer neutrons are often preferred in concept, but they can require higher temperatures, more difficult confinement, or rarer fuels. The trade remains easier. Reactions tend to be harder to manage in a vehicle because of neutron production and shielding needs. Confinement and stability become the next inward layer. On Earth, fusion experiments require elaborate devices to confine plasma, a hot ionized gas. Using magnetic fields or inertial compression, these devices struggle with instabilities where plasma moves and breaks confinement, cooling the reaction region and damaging walls. A spacecraft engine would face similar instabilities, but without the possibility of frequent maintenance. It would need long-life magnets, likely superconducting to reduce power loss, and cryogenic systems to keep them cold. Cryogenic systems add complexity and continuous power draw. The engine would also need robust first wall materials to tolerate heat and particle bombardment. The more power the engine produces, the more severe these stresses become. Thermal management returns as a strict barrier. Even if a fusion engine converts a substantial fraction of its energy into directed exhaust, a remaining fraction becomes waste heat in coils, structure, and shielding. That heat must be radiated away. At high power levels, radiators again grow large. If the craft moves at high speed through the interstellar medium, radiators and exposed structures must also withstand particle impacts and erosion. The craft thus faces a combined environment internal heat that must escape, and external impacts that threaten the surfaces used to escape it. What is known is that fusion offers high theoretical performance, and that the underlying physics of fusion energy release is well established. What remains uncertain is whether a practical, lightweight, reliable fusion engine can be built with a power-to-mass ratio sufficient for meaningful interstellar acceleration, and whether it can operate for years without failure. It also remains uncertain whether ramjet-style collection of interstellar hydrogen can ever be efficient enough to overcome Dragon engineering limits. Studies indicate severe challenges in scoop size, field strength, reaction rate, and heat removal, and no demonstrated system exists that resolves these constraints at the needed scale. Within this region, fusion is neither a simple solution nor a distant fantasy. It is a plausible energy source with known physical basis and unknown engineering maturity. The ramjet concept highlights the desire to use the interstellar medium itself as fuel, turning the void into a resource. Yet the void is thin, the fuel is reluctant, and the machinery required to harvest and burn it threatens to become so large and power-hungry that it undermines the very mass savings it seeks. The energy barrier therefore shifts inward again, from the ability to release energy to the ability to control and direct it in a compact system that remains stable, cool, and intact, while it tries to accelerate through the sparse gas between stars. Light itself can become a means of propulsion, not because it carries mass, but because it carries momentum. When photons strike a surface and are absorbed or reflected, they transfer momentum. The force is small, yet it is real and measurable. In the vacuum of space, where even small forces can accumulate over time, this photon pressure offers a way to push a spacecraft without onboard propellant. The energy source can remain far away, and the spacecraft can be designed mainly as a payload attached to a thin sail. The basic idea of a light sail is simple. A large, lightweight surface is oriented so that incoming light pushes it. Sunlight can provide this push, and the sail can slowly gain speed by continuously absorbing momentum from solar photons. Yet sunlight is spread out and weakens with distance from the sun. For interstellar ambitions, the idea evolves into a more focused scheme. A powerful laser or microwave beam is directed at the sail from a distant station. The beam carries energy and momentum. The sail captures the beam and converts some of the momentum into a steady push. If the beam remains well aimed and sufficiently intense, the sail can accelerate rapidly compared with solar sailing. The first inward barrier is the scale of the energy source. To accelerate even a small payload to a significant fraction of the speed of light within a reasonable time, the beam must deliver enormous power. The precise requirement depends on sail mass, reflectivity, beam wavelength, and the desired acceleration profile, even without calculations. The principle is clear. The force from photon pressure is proportional to the beam power divided by the speed of light. Because the speed of light is very large, the force per unit power is small. This means that meaningful thrust requires very high power. The beam system becomes a major industrial project. It must collect energy, convert it into coherent radiation, and project it in a narrow direction for long periods. A second barrier is beam focusing and spreading. Any real beam diffracts and spreads with distance. The spread depends on wavelength and the size of the emitting aperture. A shorter wavelength and a larger aperture can produce a narrower beam that stays concentrated over longer distances. Yet shorter wavelengths can be harder to generate at extreme power levels and can interact more strongly with materials, causing heating and damage. Larger apertures require immense structures, precise alignment, and stable control. Over interplanetary and interstellar distances, even tiny pointing errors can cause the beam to miss the sail. Maintaining alignment requires accurate tracking of a rapidly accelerating target, compensation for delays in control signals, and correction for disturbances in the beam source platform. The sail itself becomes the next inward barrier. A sail must be extremely light to benefit from photon pressure. It must also be robust enough to survive intense illumination. If the beam power is high, the sail can heat quickly. Even a highly reflective sail absorbs some fraction of the incoming energy. That absorbed energy becomes heat. In vacuum, the sail can only radiate the heat away. If it heats beyond material limits, it can warp, tear, or vaporize. Sail materials must therefore have high reflectivity at the beam wavelength, low mass per unit area, and stability under heating and radiation. They must also resist damage from micrometeoroids and from the sparse but energetic particles of the interstellar medium once the craft is at high speed. Sail stability is another constraint. A thin sail can crumple, ripple, or spin. If the sail's shape changes, the reflected beam can produce unwanted torques that change orientation and reduce effective thrust. Some designs rely on the beam itself to stabilize the sail by shaping the intensity profile. Others propose stiffening structures, rotating sails for tension, or active control surfaces. Each method adds complexity and mass. Mass reduces acceleration. Complexity adds failure points. The sail therefore becomes a delicate compromise between lightness and control. A beamed sail concept also shifts where the energy barrier sits. The spacecraft carries little fuel, but the infrastructure must deliver vast energy from the origin. That energy must be sustained over the acceleration period. If the goal is to reach high speed, acceleration may need to continue until the craft is far from the beam source. As distance grows, beam spread reduces intensity. Either the beam power must increase, or the aperture must be larger, or the acceleration must end earlier. Ending earlier means a lower final speed unless acceleration is very high near the source. Very high near-source acceleration increases mechanical stress on the sail and payload. There are also environmental limits near the origin. If the beam originates near Earth, it must avoid damaging satellites and spacecraft. It must avoid unacceptable heating of the atmosphere if it passes through it. Space-based arrays can reduce atmospheric issues, but they require launch and assembly. They must also manage their own waste heat. A high-power laser array converts input energy into a coherent beam with some efficiency, and the remaining energy becomes heat that must be radiated away. The array thus faces the same thermal management challenges as onboard power systems, but at far larger scale. Radiators and thermal control infrastructure become part of the beam station, not part of the ship. The energy barrier is displaced outward into an industrial architecture. The sail approach also changes the question of arrival. A laser sail can accelerate outward effectively, but slowing down at the destination is difficult if the beam source remains behind. Some proposals suggest using a sail that can also act as a brake by interacting with the destination star's light or wind, or by using magnetic interaction with the interstellar medium. Others propose a second beam source at the destination, which implies either pre-existing infrastructure or a staged mission that first sends equipment. Without effective braking, Many sail missions become flybys, collecting data during a rapid pass through a star system. Flybys can still be scientifically valuable, but they limit the depth of exploration. What is known is that photon momentum is real, and that light sails can work at small scales. Experiments and space demonstrations have shown solar sailing as a feasible method for certain missions. What remains uncertain is the engineering feasibility of scaling beamed propulsion to the power levels and aperture sizes required for rapid interstellar probes, and of building sails that can survive and remain stable under extreme illumination and long-duration exposure. These uncertainties are practical rather than fundamental, but they are severe because they involve materials, precision control, and massive infrastructure. Within this region, light propulsion highlights an important path through the energy barrier. It suggests that a spacecraft does not need to carry its energy if the energy can be supplied remotely. It also reveals that remote energy supply does not eliminate cost. It moves cost into beam generation, beam control, thermal management, and sail survival. The energy barrier remains, but it takes a different form, not a heavy ship hauling fuel, but a civilization building a powerful, precisely aimed light machine and pairing it with an ultralight structure that must stay intact while it is pushed across the darkness between stars. The beam is silent, the sail is thin, and the constraint is still energy, now expressed as power and precision concentrated into a narrow path through space. Antimatter enters the discussion as a limit case for energy density. When matter and antimatter meet, they annihilate and convert much of their mass into energy. This is not a metaphor. It is a process observed in particle physics, where electrons and positrons annihilate into photons, and where other particle pairs can do the same. The energy released per unit mass is far beyond chemical or nuclear reactions, because it draws directly on the mass energy of the particles. In principle, a small amount of antimatter contains enough energy to accelerate a spacecraft of very high speed, if that energy can be converted into directed thrust. The first inward barrier is production. Antimatter exists naturally in tiny amounts, created in high-energy processes such as cosmic ray interactions, and it can be produced in laboratories using particle accelerators. Yet producing antimatter is extremely inefficient in terms of input energy, and the quantities produced are minuscule. The process requires accelerating particles to high energies and colliding them to create particle-antiparticle pairs. Most of the input energy does not end up stored as antimatter mass. It ends as heat, radiation, and kinetic energy of many other particles. The net result is that antimatter is extraordinarily expensive in energy terms, and producing macroscopic quantities would demand vast power and industrial capacity. Even if production was scaled up, storage becomes an equally severe barrier. Antimatter cannot touch ordinary matter without annihilating. It must be held in vacuum and confined by electric and magnetic fields. For charged antimatter such as positrons or antiprotons, electromagnetic traps can confine particles in small quantities. These traps require stable fields and careful cooling to prevent particles from escaping. For neutral antimatter such as antihydrogen, confinement is more difficult because neutral atoms do not respond strongly to electric fields and require magnetic field gradients and very low temperatures. The storage of large amounts would demand large, reliable confinement systems, likely involving superconducting magnets and cryogenic cooling, both of which require continuous power and add mass. The third barrier is safety and control. Annihilation releases energy in forms that are difficult to manage. Some reactions produce high-energy gamma rays, which are penetrating and hard to reflect or absorb without heavy shielding. Others produce charged pions and other particles that can, in principle, be directed by magnetic fields. A propulsion concept might aim to channel charged products backward to create thrust, yet a fraction of the energy will still emerge as radiation that cannot be directed easily. That energy becomes waste heat and radiation exposure for the spacecraft. Shielding against gamma rays is heavy because it relies on dense materials. Dense materials add mass. Mass reduces the acceleration advantage of antimatter. Turning annihilation energy into thrust therefore becomes a conversion problem. A rocket needs momentum exchange. If the energy appears mostly as photons, the best-case thrust is limited by photon momentum, which is small per unit power, as in light sails. If the energy appears in charged particles, magnetic nozzles might direct them. Yet magnetic systems large enough to handle the particle energies and fluxes would be heavy and complex. The exhaust must also avoid destroying the engine. The products of annihilation can be extremely energetic, and interacting them with material walls would deposit heat and cause damage. A well-designed magnetic nozzle aims to keep particles away from walls, but maintaining stable confinement and direction under high power is difficult. A further inward constraint is that antimatter propulsion, if used for high-speed interstellar travel, faces the same thermal management issues as other high-power systems. Even if only a small fraction of the annihilation energy turns into waste heat, the total power might be so large that the waste is still immense. The spacecraft must radiate this heat away. Radiator requirements grow with waste power. At relativistic travel speeds, exposed radiators also face increased particle impact energy from the interstellar medium. The ship becomes a system that must keep its own high-energy core from overheating, while moving through a sparse but damaging environment. There is also the operational problem of metering. A propulsion system must release energy in a controlled way, not all at once. Antimatter stored for propulsion would need to be injected into a reaction chamber in small amounts, mixing with matter in a controlled region. The resulting particle spray would need to be directed. The injection and containment systems must prevent accidental contact between stored antimatter and the craft's structure. Any loss of confinement could lead to localized annihilation and catastrophic damage. Redundancy and fail-safe mechanisms can reduce risk but add mass and complexity. What is known is that antimatter annihilation provides the highest energy density of any known reaction. It is also known that antimatter can be produced and stored in extremely small quantities for short times in laboratory conditions. What remains uncertain is whether production can ever be scaled to the quantities needed for propulsion at reasonable energy cost, and whether storage can be engineered with sufficient stability, low mass, and long life for a spacecraft. It also remains uncertain whether a practical annihilation-based engine can direct enough of the reaction energy into thrust without requiring prohibitive shielding and radiators. In comparisons among propulsion concepts, antimatter often appears as a theoretical ideal, energy is abundant per unit mass, so the craft does not need to carry huge fuel tanks. Yet the energy barrier reappears as infrastructure and confinement. Producing antimatter demands enormous energy investment up front. Storing it demands continuous power, cryogenics, and strong magnetic fields. Using it demands systems capable of handling extreme particle energies and radiation. The ship becomes not a simple engine with a powerful fuel, but a delicate containment and conversion apparatus whose failure modes are severe. Within this region, antimatter stands as an example of how the energy barrier can be moved from the fuel's energy content to the human ability to gather, store, and control that content. The physics of annihilation is clear, but the engineering and economics are far from resolved. Antimatter does not erase the need for careful momentum exchange. heat rejection, and shielding. It only offers the possibility of meeting those needs with less fuel mass, at the price of enormous complexity and prior energy investment. The barrier therefore tightens again around control, not just supply. The question is not whether antimatter contains enough energy. The question is whether that energy can be made usable for propulsion in a stable, safe, and lightweight system that can endure the long, quiet passage between stars. When propulsion is limited by the energy that can be carried or delivered to a single craft, another strategy appears that changes the scale of the mission rather than the physics of motion. The strategy is to reduce the cost of reaching many destinations by distributing the task across many machines. A probe can be made small, simple, and focused on replication rather than on carrying large payloads. If it can use local resources at its destination to build copies of itself, then the initial launch energy is spent not to deliver a complete fleet, but to seed a process of expansion. This concept is often associated with self-replicating machines, sometimes called von Neumann probes, after an early theoretical treatment of self-reproduction in systems. The core idea is that a probe arrives in a star system, gathers raw materials from asteroids or other bodies, processes those materials into components, and assembles new probes. The new probes then depart to other systems, where they repeat the cycle. The interstellar medium remains difficult to use as fuel or feedstock because it is thin, but within a star system there are concentrated solids and metals, and there is usually a steady supply of energy from the local star. The first inward layer of the energy barrier in this approach is the shift from single mission energy to generational energy. Instead of accelerating one massive craft to a very high speed, the initial mission accelerates a smaller seed craft. A smaller craft requires less total energy to reach a given speed. This does not change the fundamental scaling of energy with velocity. It changes the mass term in the energy accounting. A tiny probe can be sent faster for the same energy budget, or it can be sent at moderate speed using a manageable fraction of planetary resources. In this way, replication reframes the energy barrier as a matter of multiplication over time rather than a single heroic leap. The second inward layer is time. Replication trades travel energy for development time in the destination system. A probe that arrives must not only operate its instruments, it must build an industrial base. Mining, refining, manufacturing, and assembly take time. They also require a stable power supply and reliable machinery. If this process takes years or decades, the overall expansion speed of the network depends on both travel time and replication time. A probe that travels fast but replicates slowly may spread no faster than a probe that travels more slowly but replicates quickly. The energy barrier is therefore redistributed into a combined cycle time that includes both propulsion and in situ manufacturing. The third inward layer is complexity. A self-replicating probe must carry more than sensors and a transmitter. It must carry tools for exploration, resource identification, excavation, and processing. It must handle diverse materials, from metals to silicates, and produce components such as structures, power systems, computing hardware, and propulsion units. It must either carry templates and specialized parts that are difficult to manufacture locally, or develop methods to fabricate them from available materials. This requirement grows severe for high-precision components such as microelectronics. On Earth, microelectronics manufacturing relies on extremely clean environments, specialized chemicals, and fine lithography. Creating similar capabilities in an autonomous, compact system is a daunting engineering challenge. If the probe cannot manufacture complex parts, it must carry them, which raises mass and reduces achievable speed. If it can manufacture them, the probe must carry a much larger industrial toolkit and a more complex control system. Energy supply within the destination system becomes central. The local star provides a constant flux of light, and sunlight can power large structures if the probe can build arrays. If the probe can mine and process materials, it can build solar collectors with large area, and then use that power to drive manufacturing and to charge energy storage systems. Nuclear fission could also be used if suitable isotopes are available and if the probe can build reactors. In either case, replication depends on the ability to convert local energy into ordered work, and it depends on thermodynamic constraints similar to those faced by spacecraft. Manufacturing produces waste heat. Refining and smelting require high temperatures. Chemical processes require controlled conditions. The probe must manage heat with radiators or by coupling to local bodies, and it must handle the mechanical wear and corrosion that occur in processing equipment. The energy barrier does not vanish. It becomes a steady industrial challenge in an alien environment. The environment offers both help and hazard. Asteroids provide concentrated metals and minerals. Many are loosely bound rubble piles, which can be easier to mine than a planet's surface. The low gravity helps with transport but complicates containment of dust and debris. Dust can foul machinery and contaminate sensitive components. A probe operating for years must protect its moving parts and its optical systems. It must also resist radiation and impacts. In a star system, charged particle environments and micrometeoroid flux can be significant. If replication depends on delicate manufacturing steps, the probe must create controlled spaces, shielding, and perhaps pressurized enclosures. Building and maintaining such environments adds mass and energy requirements. There is also the question of error control. Replication must preserve function across generations. In biological systems, error correction exists in copying and repair. In machines, error control would require quality assurance, testing, and calibration. Each generation must build parts within tolerance and assemble them correctly. If errors accumulate, later generations may fail. This introduces a need for robust metrology, standardization, and adaptive repair. Such systems can be designed in principle, but they add computational and mechanical complexity. They also add power demands, because measurement and testing require energy and time. Communication and coordination add another inward constraint. A network of probes spreading through space would have long communication delays. Coordination from a central origin would be limited by light travel time. This implies that each probe and each local factory must operate with high autonomy. Autonomy requires software that can handle unexpected material properties, machine failures, and environmental hazards. Software robustness is not guaranteed. It depends on careful design, testing, and the ability to update. Updating across interstellar distances is slow. A probe might need to carry its own capacity for self-diagnosis and self-modification. This raises further questions about reliability over long periods. What is known is that self-replication is consistent with physics in principle. There is no physical law that prevents an automated system from building a copy of itself, given sufficient materials, energy, and information. What remains uncertain is whether such replication can be achieved with compact, autonomous systems, especially for high-technology components, and whether it can be made robust against failure across many generations. The uncertainties are not small. They involve manufacturing, control, software, and the unpredictability of operating in varied star systems. In the context of the energy barrier, Self-replicating probes offer a different kind of efficiency. They reduce the need to launch large masses repeatedly from a planetary gravity well. They allow a civilization to invest energy once in a seed mission, and then rely on local energy at each destination for further expansion. This shifts the dominant energy expenditure from propulsion fuel carried across interstellar space to industrial energy harvested locally. The barrier becomes less about the peak energy of a single launch, and more about the total energy and time invested across a spreading process. This strategy also changes what is meant by success. A probe that is designed for replication might carry only limited science instruments. Its main purpose might be to establish presence and capability. Science could be conducted by later generations with specialized payloads built locally. Alternatively, replication could be used to build communications relays, making later missions easier. These possibilities show that the energy barrier can be approached indirectly, by building a distributed infrastructure over time rather than demanding immediate, high-speed travel for large crews or heavy payloads. Within this region, the inward movement is from propulsion to logistics. The energy barrier is acknowledged as a constraint on moving mass quickly. Replication responds by minimizing the mass that must be moved, and by multiplying capability at the destination. The approach does not promise a simple path to human travel, because humans require large life support systems and strict safety. Yet it offers a plausible way to extend exploration reach without requiring each mission to carry a civilization's worth of energy in one vehicle. The darkness between stars remains wide, but the burden of crossing it can be distributed across many small crossings, each one powered by careful energy use and followed by long, quiet work in the light of a new star. Even with advanced engines and clever strategies, travel that remains below the speed of light stays confined by a quiet geometry of time and distance. A spacecraft can accelerate, coast, and perhaps brake, but every leg is measured against the same constant that governs signals and causality. This does not mean that interstellar expansion is impossible. It means that it proceeds as a front that moves outward at a finite pace, and that pace is set by the best sustainable cruise speed a civilization can achieve for its chosen payloads. The energy barrier therefore appears as a limit on how quickly a sphere of influence can grow, even when the work is spread across many missions. In this region, the picture is not of a single ship but of many launches over long spans. A planetary civilization might send probes first, then larger robotic craft, then perhaps habitats or slow-moving arcs. Each mission takes time to prepare, time to travel, and time to use what it finds. Even if the departure world can launch frequently, the receiving world cannot respond instantly because signals and ships both require years to cross interstellar space. The result is a pattern in which decisions propagate outward slowly, knowledge returns slowly, mistakes are corrected slowly. This slowness is not a cultural weakness, it is a property of the distances involved. At sublight speeds, the closest stars are reachable within times that can be meaningful on human historical scales, but only if the cruise speed is high enough. A speed of a few tens of kilometers per second, common for many solar system probes, turns a journey of a few light years into tens of thousands of years. A speed of a few thousand kilometers per second turns it into centuries. A speed that is a noticeable fraction of the speed of light turns it into decades. Each step upward in speed demands steeply rising energy. The energy barrier, therefore, does not merely determine whether travel is possible. It determines whether travel is fast enough to support sustained interaction, trade, or governance between star systems. If journeys take millennia, each system becomes effectively isolated on the timescale of human institutions. If journeys take decades, slow connections become possible, but only for a civilization willing to plan over lifetimes. The limit of sublight expansion becomes clearer when considering a chain of settlements. Imagine an origin world that sends a mission to a nearby star. That mission takes time to arrive and establish itself. The new settlement then sends missions onward. Over time, a wave of expansion can proceed, each step taking a travel time plus a development time. The development time includes building energy infrastructure, manufacturing capability, and reliable launch systems in a new environment. Even in optimistic scenarios, this adds years or decades. The outward speed of the expansion front is therefore slower than the cruise speed of the ships, because ships do not depart from a destination the moment they arrive. They depart after work is done. This introduces an important practical ceiling. A civilization can have very fast ships, but if the ships require enormous energy investment, the launch rate might be low. A single high-speed ship might be possible once in a long time, like a rare global project. Expansion then proceeds not as a smooth wave but as sparse jumps. Alternatively, a civilization might choose slower ships that are cheaper, allowing many launches. The expansion front might then be steadier even if each ship is slower. The energy barrier thus shapes not only speed but strategy. A civilization chooses between rare, fast missions and frequent slow missions, constrained by total energy production and by industrial capacity. Even when many missions are launched, communication remains bound to light travel time. A message from a system 10 light-years away takes 10 years to reach the origin. A reply takes another 10. Policy, coordination, and shared culture become stretched across time. Decisions made at the origin arrive late and may be irrelevant to local conditions. Local societies may diverge in language, norms, and technology. This divergence is not speculative in detail. It follows from the simple fact that frequent feedback is impossible across large distances when information cannot travel faster than light. The energy barrier indirectly reinforces this separation because it discourages ships from routinely traveling at speeds near the light limit, which would reduce travel times but demand extreme energy and protection. Sublight travel also interacts with the environment in a way that limits practical speed. A craft moving at high speed through the interstellar medium experiences impacts from atoms and dust grains that carry increasing kinetic energy. At low speeds, the medium is a gentle drag and a minor erosion source. At higher speeds, it becomes a source of heating, radiation, and mechanical damage. Shielding can reduce risk, but shielding adds mass. Active deflection might be possible for charged particles, but neutral dust remains difficult to deflect without massive fields or sacrificial structures. The faster the craft, the more severe the damage from even tiny grains. This turns high-speed interstellar travel into a contest between the desire to shorten time and the need to survive the path. The energy barrier becomes not only the energy to accelerate but also the mass cost of protection, and that mass cost grows with the chosen speed. A sublight expansion also faces a limit in the distribution of energy resources. Near the origin, infrastructure is dense. As the frontier spreads, each new system must build its own energy collection and manufacturing base. The ability to do so depends on the local availability of materials, the stability of orbits, and the hazards of the system, such as radiation belts and frequent impacts. Some systems may be rich in asteroids and stable energy sources. Others may be less convenient. An expansion front can stall or slow if it encounters regions where suitable targets are far apart or resources are difficult to access. This is not a barrier set by fundamental physics, but it is a barrier that arises from the uneven structure of real star systems. Over longer distances, the structure of the galaxy becomes relevant. Stars are not evenly spaced. In the Sun's neighborhood, nearby stars are separated by a few light years, but the density changes with location in the galaxy. The disk contains gas, dust, and spiral structure. There are regions with higher stellar density and regions with lower. A civilization expanding at sublight speed would find that some routes offer shorter hops, and others require longer crossings. Longer crossings demand higher speed or longer travel time. Higher speed demands more energy and more shielding. Again, the energy barrier shapes the path that seems feasible. This region also reveals an upper bound on how much the past can remain connected to the present. If expansion proceeds for thousands of years, the origin world becomes a distant historical point. Even if ships continue to travel, the time delays mean that no central authority can respond quickly to far events. No shared market can react quickly to supply and demand shifts across many light years. The result is a network that may share ancestry and occasional exchange but lacks tight integration. The energy barrier contributes because it makes routine, high-speed travel costly, limiting the frequency and mass of interstellar traffic. What is known is that sublight travel permits expansion in principle, because no physical law prevents a spacecraft from traveling between stars at speeds below the speed of light. It is also known that the timescales and energy costs rise quickly as the desired speed increases. What remains uncertain is how far engineering can push practical cruise speeds for meaningful payloads while keeping systems safe, cool, and reliable. It remains uncertain whether future materials, power systems, and shielding concepts can allow sustained travel at speeds that make interstellar exchange common rather than rare. These uncertainties are bounded by thermodynamics, by the need to reject waste heat, and by the harshness of high-speed travel through even a sparse medium. Within this region, the limit of sublight expansion is not a single number. It is a shape of history. It is the slow outward movement of capability, the gradual establishment of new energy islands around new stars, and the widening gaps of time between causes and effects. The energy barrier is present in every ship's fuel and every station's power plant, but its deeper consequence is pacing. It sets how quickly the frontier can move, how tightly distant systems can remain linked, and how the galaxy, vast and structured, turns interstellar travel into a long sequence of patient crossings rather than a quick opening of space to routine motion. When the discussion turns from propulsion to curved spacetime, the energy barrier takes on a different tone, because it becomes tied to the geometry of gravity rather than to the direct acceleration of a ship through space. General relativity describes gravity not as a force in the usual sense, but as curvature of space-time caused by mass and energy. Objects move along paths called geodesics, which are the natural straight lines of curved space-time. This framework explains planetary orbits, the bending of light near massive bodies, the existence of black holes, and the expansion of the universe. It also allows, in principle, geometries where two distant regions of space are connected by a shorter path through space-time than would be available in ordinary flat space. In this region, the aim is not to push a ship faster and faster. The aim is to alter the path itself so that the ship's journey, measured along the altered geometry, becomes shorter. If such a geometry could be created or accessed, a ship might reach a distant destination while locally moving at sublight speed, obeying the speed limit at every point. The ship would not outrun light in its immediate neighborhood. Instead, the space between origin and destination would be shaped so that the effective travel time could be reduced from the perspective of distant observers. This idea is often described as a shortcut, and it is associated with concepts such as wormholes and with other proposed spacetime configurations. The first inward barrier is that general relativity links spacetime curvature to energy and momentum through its field equations. Creating a significant curvature change is not a matter of clever machinery alone. It requires mass-energy arranged in specific ways. Ordinary matter produces curvature in familiar forms. Planets, stars, and galaxies curve spacetime. Yet the curvature produced by even massive objects is not typically shaped into a controlled corridor that connects distant regions. The natural curvature of a star causes nearby orbits and slight bending of light, but it does not create a tunnel through spacetime. To produce exotic geometries, theoretical studies often find that unusual energy conditions are needed. A key concept here is negative energy density, sometimes described as exotic matter in theoretical contexts. In many solutions that resemble traversable wormholes or spacetime warp configurations, the stress energy required includes regions where energy density is negative relative to certain observers, or where pressures and stresses violate conditions that ordinary matter usually obeys. In classical physics, energy density is non-negative for normal matter. In quantum physics, there are situations where effective negative energy can appear in limited ways, such as in the Casimir effect between closely spaced conducting plates. Yet these effects are small, local, and constrained by quantum inequalities that limit how much negative energy can exist, for how long, and over what region. These constraints suggest that even if negative energy is possible in principle, creating it in the amounts and configurations needed for macroscopic spacetime engineering may be far beyond practical reach. The second inward barrier is stability. Even if a spacetime configuration resembling a wormhole could exist, it must be stable against collapse and against perturbations. Many wormhole solutions in general relativity either collapse quickly or require constant maintenance by exotic stress energy. A small disturbance could cause the throat to pinch off, turning the configuration into a black hole or a singular structure that cannot be traversed. The physics of such stability depends on the matter and fields that support the geometry. Because those supporting ingredients are not known to exist in controllable forms, stability remains uncertain. This is not a mere engineering gap. It is a gap in demonstrated physical possibility at macroscopic scales. The third inward barrier is energy requirement in another form, the scale of curvature needed to affect interstellar distances. A minor space-time distortion near a ship does not change the vast separation between stars. To reduce travel time substantially, the geometry would need to be altered over a large region, or in a way that connects distant points. The mass energy associated with such curvature could be enormous. In some theoretical estimates, the energy required to create a bubble or tunnel could be comparable to the mass energy of astronomical bodies. These estimates depend on the chosen model and assumptions. The precise numbers vary, and there is uncertainty. Yet the common feature is that the required stress energy is not modest. It sits far beyond the capabilities of a planetary civilization, and likely beyond anything short of star scale or larger control, if it is possible at all. General relativity also places strict constraints on causality. Spacetime shortcuts can introduce the possibility of closed time-like curves, paths that return to the past in a way that creates paradoxes. Many physicists take this as a sign that such configurations are either unphysical or prevented by deeper principles not yet fully understood, sometimes called chronology protection. This remains an area of theoretical investigation. There is no experimental evidence for macroscopic wormholes or warp-like geometries, and there is no established mechanism for creating them. Observationally, The universe appears well described by general relativity and by standard forms of matter and energy on large scales, without signs of engineered or naturally occurring traversable shortcuts nearby. Within the known universe, gravity does offer one kind of shortcut that is real, but limited gravitational assists and gravitational slingshots. A spacecraft can use a planet's motion to change speed and direction without spending propellant. This is an exploitation of curved spacetime in a practical Newtonian approximation. Yet it does not change the interstellar distance problem. It is useful within a star system where planets are available. Beyond, there are no conveniently placed massive bodies along a direct path. The energy barrier remains, and gravity assist cannot bridge the gap. There is also the reality of gravitational time dilation. Clocks run at different rates in different gravitational potentials. Near a massive body, time passes more slowly relative to far away. This effect is measurable and important for satellite navigation systems around Earth. Yet using gravitational time dilation as a travel aid does not reduce the energy needed to move between stars. It only changes how time is experienced relative to distant observers. A ship lingering near a black hole could, in principle, experience less proper time while distant time advances, but the ship would still need to travel to the black hole and then away again. The energy costs and hazards would likely be extreme, and the geometry does not provide a simple route to a chosen distant star. What is known is that general relativity permits a rich set of spacetime geometries mathematically. It is also known that many of these geometries require stress energy conditions that are not known to be achievable with ordinary matter. It remains uncertain whether quantum gravity, a more complete theory that unites general relativity with quantum mechanics, would permit stable, traversable shortcuts, or forbid them. It also remains uncertain whether the universe contains naturally occurring shortcuts that could be used, though none have been observed. In this region, the energy barrier becomes intertwined with the deepest questions about gravity and matter. The propulsion problem becomes a geometry problem, and the geometry problem becomes a matter problem. The hope of reducing travel times by reshaping space-time confronts the requirement for exotic energy distributions, the risk of instability, and the scale of mass energy likely required. The result is a sobering perspective. The most dramatic shortcuts in theory do not come cheaply. They demand control over forms and quantities of energy that remain outside demonstrated physics and engineering. The barrier remains an energy barrier, now expressed not as fuel for engines but as the stress energy needed to shape spacetime itself. At the innermost region of the topic, the energy barrier to interstellar travel is no longer a single obstacle that can be named and then bypassed. It is a coupled system of requirements that pull against each other: energy source, propulsion method, shielding, heat rejection, structure, guidance, and mission duration. Each requirement feeds the others. More power enables faster acceleration, but it raises waste heat. Larger radiators remove heat, but they add mass and vulnerability. More shielding improves survival at high speed, but it adds mass and increases the energy needed to reach that speed. Carrying more propellant can enable braking and course correction, but it increases starting mass and therefore increases the energy and thrust required for departure. The barrier is the closed loop itself. At the center lies the relationship between mass and energy. A spacecraft is a physical object with inertia. To change its motion significantly, it must exchange momentum. In the absence of external momentum exchange, it must expel reaction mass. If it seeks very high speed, the kinetic energy demanded becomes enormous, and the energy required rises steeply with speed, even before relativistic effects intensify the cost. If it seeks to approach the speed of light, Special relativity adds another tightening. Each additional increment in speed requires disproportionately more energy. This is not a technical limitation. It is a structural feature of the universe as presently understood. The ship can approach light speed, but the cost of approaching becomes increasingly severe. Energy sources then set the first practical ceiling. Chemical sources are far too limited for relativistic ambitions. Fission can provide high energy density and steady power, but burdens the craft with radiation, shielding, and heat rejection. Fusion promises higher performance but remains unproven as a compact, reliable propulsion system with high power-to-mass ratio. Antimatter offers extreme energy density but faces formidable barriers of production, storage, and safe conversion of annihilation energy into thrust. Beamed propulsion shifts energy production off the craft, but demands vast infrastructure and precision, and it complicates arrival. Space-time shortcut ideas depend on forms of stress energy not known to be achievable, and on stability conditions that remain uncertain. Each option changes where the barrier sits, yet none remove it. The barrier changes shape, but it remains energy plus control. Thermal physics forms the next inward clamp. Any real system that produces power also produces waste heat. In space, waste heat leaves mainly by radiation. Radiators therefore become fundamental components of high-power spacecraft. Their size is set by how much heat must be rejected and by the temperature the system can tolerate. High temperatures allow smaller radiators, but high temperatures push materials toward failure and can worsen radiation damage. Low temperatures protect materials but demand larger radiators and more mass. If the craft accelerates for long durations, the radiator system must function reliably for long durations. If the craft travels at high speed, the radiators must also survive impacts and erosion. The energy barrier thus includes not only the ability to generate energy, but also the ability to dispose of it safely. Protection is another central clamp. The interstellar medium is sparse, yet at high speed even a tiny grain carries large kinetic energy. Charged particles and cosmic rays penetrate materials and damage electronics, while high-speed collisions can vaporize surface layers. Protection can take the form of shielding, sacrificial layers, electromagnetic deflection for charged particles, and careful spacecraft geometry that places sensitive systems behind mass. Each method adds mass or complexity. For crewed travel, protection becomes stricter because biological tissue is vulnerable to radiation, and because life support systems cannot tolerate severe damage. The energy barrier rises sharply for crewed missions not because human bodies are heavy, but because keeping them safe demands mass, volume, redundancy, and stable power. Reliability tightens the barrier further. Interstellar travel is long-duration operation far from repair. Systems must tolerate component failures, radiation-induced errors, and gradual material degradation. Redundancy helps but increases mass. Autonomy helps but demands computing, sensors, and robust software, which require power and heat management. Long missions must also maintain attitude control, navigation accuracy, and communication. Each of these needs steady energy. A small continuous power draw becomes a large total energy requirement over decades. Reliability therefore converts time into energy demand and converts energy into mass demand, because more energy usually means more power systems and more thermal systems. Arrival forces the most honest accounting. A mission that does not break can be simpler in some respects, because it can spend energy only on departure and cruise. Yet flyby science is limited by time at the target. If the mission seeks to enter orbit around a planet in another star system, or even to slow enough for extended observations, it must shed enormous kinetic energy. If the ship carries propellant for braking, it must launch with that propellant, increasing starting mass and raising departure energy. If it uses external braking methods, those methods demand either interaction with local environments in ways that remain uncertain, or the existence of infrastructure at the destination. The energy barrier therefore includes both halves of the journey. Speed gained must be speed managed. When all couplings are seen at once, a practical picture emerges. For small probes, high speeds might be approached through beamed propulsion or advanced nuclear systems, because the mass term can be reduced and the mission can accept flyby arrival. For larger payloads, especially for human travel, the protective and life support mass rises and the thermal and reliability requirements grow. The same speed that might be plausible for a gram-scale sail becomes far less plausible for a 1,000-ton habitat because energy and protection scale with mass. This difference is not a matter of optimism. It is the arithmetic of momentum, heat, and shielding. There are areas where uncertainty remains genuine. It remains uncertain how far materials science can push radiator temperatures without unacceptable mass. It remains uncertain whether fusion can be engineered into lightweight, reliable propulsion with high thrust and manageable neutron shielding. It remains uncertain whether new propulsion methods that remain consistent with known physics could emerge, such as improved beamed energy systems, better magnetic nozzles, or more efficient power conversion. It remains uncertain how autonomous manufacturing and repair might reduce the need to carry redundancy. These uncertainties matter, and they could shift what is feasible at the margins. Yet the broad structure is stable energy must be generated or delivered, directed into momentum change, and the waste must be rejected while the craft is protected and kept functional for a long time. At the center, the energy barrier can be described as a boundary of practicality rather than a boundary of possibility. Physics does not forbid crossing interstellar distances. It does, however, set a strict price in energy, and it ties that price to mass, speed, and time in ways that are difficult to escape. Every proposed path rearranges the payment. Carrying fuel pays in mass, beaming power pays in infrastructure, using nuclear energy pays in heat and shielding. Seeking space-time shortcuts pays in unresolved physics and likely extreme stress energy requirements. The inner barrier is the coupled requirement that all these payments must be made at once, by a system that must remain stable, cool, protected, and precise, while it moves through a medium that is thin but not harmless. When the accounting is complete, interstellar travel appears as an engineering ambition that sits on the edge of civilization-scale energy management. Its barrier is not only that the stars are far, its barrier is that speed is expensive, heat is relentless, and protection is heavy. The quiet lesson is that travel between stars is a test of disciplined energy control across long time, in a universe that keeps strict books and charges interest in mass, waste heat, and vulnerability. In the long, dark space between stars, the mind tends to reach for a single missing invention, as if one device could close the gap. The physics that shapes the gap instead spreads the difficulty across many linked limits. Distance stretches time. Higher speed reduces time but demands far more energy. More energy demands more power systems and more thermal control. Thermal control demands radiating waste heat into space, which requires surface area, mass, and durability. Protection against radiation and impacts demands shielding, which adds more mass. Mass then increases the energy required to accelerate and to brake. The cycle closes and tightens. A quiet way to hold this picture is to imagine the spacecraft not as a vehicle in a hurry, but as a moving balance among forces and flows. Energy enters as stored fuel or as power delivered from afar. Some of that energy becomes ordered motion, and some becomes heat that must be released. The craft is always managing gradients hot to cold, inside to outside, protected to exposed. In interstellar space, there is little to push against and little to draw from. The craft must carry its own capacity to act, and it must do so for a long time without repair. What remains most stable across all credible concepts is the need for restraint. Small probes may reach higher speeds because their mass is low and their missions can accept flyby arrival. Larger missions become dominated by the massive shielding, life support, redundancy, and heat rejection. Beamed propulsion can shift the heaviest energy systems away from the ship, but it concentrates difficulty in precision and infrastructure, and it leaves the arrival problem unresolved. Nuclear systems can provide high energy density, but they tie propulsion to radiation management and radiators that must survive the voyage. Speculative space-time shortcuts, while mathematically intriguing, sit beyond demonstrated control of the stress energy required and beyond confirmed stability, leaving them as questions for deeper physics rather than near-term routes. In the end, interstellar travel is best understood as an energy discipline practiced across distance. The barrier is not a prohibition. It is a price structure imposed by conservation, by thermodynamics, and by the realities of matter moving fast through even a thin medium. A civilization that wishes to cross to another star must decide what it values most: speed, payload, safety, or frequency. It must accept that gaining one often costs heavily in another. The stars remain reachable in principle, but they remain demanding in practice, and the demand is always expressed in energy managed with patience and care.